So let's start the Faraday's experiment. As we have discussed earlier, the actual development of electromagnetism was based on the experiments performed by Faraday. So this is, we can say, the god of electromagnetism. So starting with the experiment number 1, in this experiment 1, first of all I will give you the diametrical arrangement, and then I will explain you that what this experiment gives you about the development of electromagnetism. So this is the arrangement of experiment number 1, which was performed by Michael Faraday. So in this experiment he took a ring of soft iron and he has also taken an insulated conducting coil. The thing which is wounded or connected with the ring is the induction or conducting coil. So these are the main two parameters. Also he has connected with the battery, and this is the switch. This V what you watching in the figure I am giving you, V is for battery, means a voltage power supply. S is for switch, and this G is nothing but a galvanometer which shows the deflection. So this is for galvanometer. So this is the arrangement of his experiment. Now, the coil which is connected to a battery, means this coil will work as a solenoid, which you have studied in the semester number 3. So this is the solenoid. Now, when this switch is opened, that means the voltage will supply through this, and whenever this switch is off, there is no passing of voltage. So this situation is for passing of electric current through the coil. So when the current is passing through the coil, there is the production of magnetic field. But where does it produce the magnetic field, and how can we judge that the magnetic field is produced? So first of all, write down the event in which the voltage or current passes through the solenoid the magnetic field is produced. So here there is also you can consider the effect in which the magnetic field is produced due to the electric field. Now, when the current is passes through these, the solenoid has produced the magnetic field. But what about this coil? So, as the current is passing through the solenoid, this coil will also generate some current. And the electric current which is passing through this coil and that will be measured in galvanometer. So here the work of galvanometer is for measure the electric current passing through the coil. But here the coil is only of this side, not of the coil which is connected to the battery. Now, here we have taken the soft ring. So, the magnetic field lines which are produced that will remain in the ring. Means the magnetic field here produced is inside the ring. So anyone can be asked that at which place the magnetic field is produced in the Faraday's first experiment. Now, suppose Faraday has passed a steady electric current to the left coil, then what happens? Then no effect was observed in the galvanometer. So see, when a static current or a steady electric current means either like this, means DC type of current when passes through this, then galvanometer shows no deflection. Faraday was slightly disappointed because the effect was not working, but Faraday's intuition worked at that moment. During minute observations of every moment, he observed that galvanometer shows a slight deflection whenever the battery is switched on and switched off. So in both the cases, deflection of galvanometer was in opposite direction. So when the switch is opened like this, suppose this is your switch. At this condition, the galvanometer shows the deflection in this direction. Suppose this is your galvanometer, and whenever there is switch off, means this condition, then the galvanometer will show the deflection on this side. So the directions are totally opposite. That was the actual observation of Faraday. But when there is a steady current is passing, there is no importance of this experiment. So the limitation we can say of this experiment was not applicable steady current. Here I am writing current, but you have to understand that is electric current. Now, we will move on to the experiment number 2, in which we will actually see the effect of magnetic field. Here we have applied electric field, but now we are going to apply the magnetic field. Here the magnetic field was produced inside the ring. Now we will see in the experiment number 2 that what are the changes which we are going to see. So let's start the experiment number 2. In the second experiment, Faraday has little bit changed the arrangement of experiment number 1, in that he has used the concept of electricity, but here he has used the supply or the induction process, or we can say the induction origin is taken in terms of the magnetic field. Now, let me give you the graphical arrangement of the experiment number 2. So this is the graphical arrangement of experiment number 2, in which Faraday has arranged 2 bar magnets in V shape. See, if I rotate this figure in slightly this way, then this will be the V shape. See, bar magnet is the part of magnet, nothing else. But in V shape, but there is a north pole is connected to the south pole of the other bar magnet. See, and here is the north pole comes. So this is the actual arrangement. Then at the other end of V shape, he kept a soft iron rod. So this is the soft iron rod which is connected with the galvanometer. So this was the actual arrangement, and this galvanometer is not directly connected to the iron rod, but the wire which is wounded on the iron rod, and the wire is made up of copper. So the copper wire wounded on the iron rod. Now you will give me a question that where does the electricity comes in this particular case. So here you see the two elements, copper and iron. This copper and iron are actually having some number of protons, some number of electrons. Similarly, this iron is also having some number of protons and some number of electrons. That means some charged particles are there. So these charged particles, whenever in the motion, so they will produce the electric field, and now the event starts. That when the galvanometer shows deflection on moving the end of upper magnet up and down. See, when this upper magnet is moving to up and down, the galvanometer shows the deflection. So why it is showing the deflection? Because as the magnet moves near to the rod, then the magnetic flux linked with the coil increases. So we can write one statement like this: near to the rod, then magnetic flux, that is written as phi, linked with the coil. So phi of coil will increase. Similarly, the opposite effect when the magnet touches the iron rod. See, and this is the condition or situation which is seen in the figure. Then the magnetic flux linked to the coil will be maximum, and as the magnet moves far to the rod, then the magnetic flux linked to the coil will decrease. So these three situations are important, and we can say these are the outcome of experiment number 2. Now, from this experiment, Faraday has concluded one thing which we are going to discuss. But you see, first of all, this situation. In this situation, can you give the deflection of galvanometer? Yes, so the deflection of galvanometer will be also maximum, because this magnet has now touches the surface of iron rod. Now, the conclusion from experiment number 2. And the conclusion is, to induce electric current in a coil, so there is an electric current is passing when the magnetic field touches the rod, then the electric current is passing through the coil, and then the galvanometer shows us the deflection. Change in magnetic flux is required. So we have seen the three types of changes in the magnetic flux. And not the flux itself. We don't need the change in flux, but we need the change in magnetic flux. So with this, our experiment number 2 is also over. Now we will see the most important experiment, which is experiment number 3. So here the experiment number 3 and its arrangement is shown. In this particular figure, an insulated conducting coil, which is written here as C1, that is connected to a galvanometer. Now, we have put a bar magnet slightly at the distance of particular, and the north pole is directed towards the coil. Now, whenever the bar magnet is moving, means the north pole is coming towards the coil C1, then the galvanometer shows the deflection. So when north pole is coming towards coil C1, then galvanometer will show the deflection. And when the galvanometer shows the deflection, that means current is conducting in coil C1. And now galvanometer shows the deflection as far as the bar magnet is in motion. So if we assume that up till this distance the bar magnet is in motion, so up to this the galvanometer will show deflection, but after that the galvanometer stops to give the deflection because there is no passing of current. Means whenever the bar magnet is stationary, galvanometer will show no deflection. And also when the magnet is pulled away from the coil, so when the north pole is moving farther than coil C1, then galvanometer will show the deflection but in the opposite direction. So now the direction of current will also change. Because the deflection is in the opposite direction and hence there is also change in the direction of current. Now, if we see the same experiment in two coils, then what happens? But before that, here we have considered only north pole. But suppose the south pole is coming towards the coil C1, then there is opposite to the deflection, means the galvanometer will show the opposite deflection. Similarly, when south pole is moving farther to coil C1, then galvanometer will show the deflection in its original direction. So, in this case, the current is produced in the same direction of magnetic field. So what does this experiment suggest? The first experiment was suggesting that electric field can generate magnetic field. Now this experiment number 3, you see, the magnetic field can generate electric field also. So the experiment number 2 and 3 are for magnetic field which produce the electric field. Now, when the bar magnet is held fixed and the coil C1 is moved towards or away from the magnet, means now you put magnet as steady. In the above case you were considering the coil as steady, but now you consider the magnet as steady. Then what happens? In this case you have to change the position of coil, and whenever the coil moves towards or upwards from the magnetic field, then the effect will be same as that of we discussed in the case of bar magnet. Now, instead of taking a single coil, now my task is to find out for double coil. So here the experiment using two coils is given, in which the coil C2 is connected to coil C1, we can say they are connected or they are placed near or far to each other. Then the coil C1 will also show the displacement or deflection because of the C2 is having the current produced and this effect of current will taking place to coil C2 and hence this galvanometer will show the deflection. Now, any one of the coils C1 or C2 has been given a rotation to each other, then also the galvanometer shows the deflection. So here whenever there is no connection between coils, then galvanometer also shows the deflection. In other words, the coils means the both coils are having the production of current. Now, the result of this experiment shows that some following things. 1. The relative motion between the magnet and coil is responsible for generating electric current in the coil. So what we have concluded we are only writing now. Similarly, if the relative motion between magnet and coil, this arrow suggests relative motion, if this is increasing or decreasing, then the induced current will be more or less. Now the third one, the direction of induced current is reverse. And whenever this will be reversed, if the direction of the relative motion between magnet and coil is reversed. Now the fourth one, if the magnet and coil are moving with the same speed, then what happens? Then no current is induced in the coil because they are moving with the same speed and also in the same direction. Then there is no electric current is induced. The current produces in the coil and Faraday has given name this particular current as induced current. So this was the actual definition of induced current. Now, when the current generated in other coil, because we have seen experiment number 1 and experiment number 3 with the use of two coils. Indicates that the EMF, what do you mean by EMF? Electromotive force. EMF is produced in it. Which gives it the energy for the motion of charges. And such EMF is referred as induced EMF. And this phenomenon is called magnetic induction. So this is the basic definition of magnetic induction. Now, after such experiments of Faraday has finally concluded that the mechanical energy can be converted into electrical energy. So with this our article number 1.2 is also over. Now here you have seen word that magnetic flux, but what it is and how we can define them. So we will see it in our next class.